Welcome to this comprehensive guide on high availability architecture. In this video, we'll explore how to build fault-tolerant systems that keep applications running continuously. High availability is critical for modern cloud applications where downtime can result in significant business losses and poor user experiences. We'll cover the essential components, design principles, and best practices that enable systems to remain operational even when failures occur. By the end of this video, you'll understand the fundamental concepts needed to design always-on applications that can withstand various types of failures. High availability refers to a system's ability to remain operational and accessible with minimal downtime, ensuring continuous service delivery to users. It's measured as a percentage of uptime over a given period. 3 nines, or 99.9% availability, means approximately 8.7 hours of downtime per year. 4 nines, or 99.99%, reduces this to about 52 minutes per year. 5 nines availability, or 99.999%, is the gold standard, allowing only about 5 minutes of downtime annually. These numbers represent service-level agreements that businesses commit to, and achieving them requires careful architectural planning and redundancy. Redundancy is the foundation of high availability, focusing on eliminating single points of failure. The concept is simple: duplicate critical components so that when one fails, the system continues operating. There are two primary redundancy models. Active-active redundancy means multiple components handle requests simultaneously, distributing the load across all instances. This approach maximizes resource utilization and provides better performance. Active-passive redundancy involves a primary component handling all traffic, while a standby component remains ready to take over during a failure. While this approach uses resources less efficiently, it provides a clear failover path and is simpler to implement for certain workloads. Failover mechanisms enable automatic switching from a failed component to a backup without requiring human intervention. This automation is crucial for maintaining high availability because manual intervention introduces delays. Automatic failover detects failures and switches to backup systems instantly, often in seconds. Health checks are continuous monitoring processes that validate whether each component is functioning properly. These checks run at regular intervals to detect problems before they impact users. Fast detection is essential because the quicker you identify a failure, the less downtime users experience. Modern systems use sophisticated health checks that monitor not just whether a component is running, but whether it's responding correctly and performing within acceptable parameters. Load balancing distributes incoming traffic across multiple servers to prevent any single server from becoming overloaded and to ensure optimal performance. Several algorithms determine how traffic is distributed. Round-robin distributes requests sequentially across all available servers, ensuring even distribution in most cases. Least connections routes traffic to the server with the fewest active connections, which works well when requests have varying processing times. Weighted distribution allocates traffic based on server capacity and performance, allowing more powerful servers to handle proportionally more requests. Health-based routing directs traffic only to healthy, responsive servers, automatically removing failed servers from the rotation. Load balancers continuously monitor server health and adjust routing decisions in real time. Continuous monitoring and alerting track system health with real-time notifications, enabling proactive issue resolution before failures impact users. Health metrics include CPU utilization, memory consumption, disk space, and network bandwidth usage. These fundamental metrics indicate whether servers are operating within normal parameters. Performance tracking focuses on response times, throughput, and latency, measuring how quickly the system responds to user requests. Alert thresholds trigger automated notifications when metrics exceed predefined limits or when anomalies are detected. Effective monitoring systems don't just collect data, they analyze patterns, predict potential failures, and alert operations teams before issues become critical. This proactive approach minimizes downtime and maintains service quality. Data replication maintains multiple copies of data across different locations to prevent data loss during failures. This is distinct from redundancy of compute resources. It specifically addresses data durability and availability. Synchronous replication writes data to all replicas simultaneously before confirming the write operation as successful. This approach guarantees data consistency, but introduces latency because the system must wait for all replicas to acknowledge the write. Asynchronous replication allows the primary database to confirm writes immediately, with replicas updated shortly afterward. This provides better performance, but introduces a small risk of data loss if the primary fails before replication completes. Multi-region replication distributes data across geographic locations, protecting against data center-level disasters and enabling disaster recovery capabilities. Graceful degradation allows a system to continue operating with reduced functionality rather than completely failing when components malfunction. This approach maintains core services while temporarily disabling non-critical features. Feature toggles disable secondary features during high load or failures to maintain core functionality. For example, an e-commerce site might disable product recommendations but keep checkout working. Circuit breakers stop requests to failing services to prevent cascade failures from spreading throughout the system. When a service fails repeatedly, the circuit breaker opens, immediately returning errors instead of attempting doomed requests. Fallback mechanisms provide alternative responses or cached data when the primary service is unavailable. Rate-limiting controls request flow to protect the system from overload, rejecting excess requests rather than allowing the entire system to collapse under load. Several design principles are essential for building highly available systems. First, eliminate single points of failure by designing architecture where no single component failure causes complete system outage. Every critical component should have redundancy built in from the start. Second, geographic distribution deploys resources across multiple availability zones and regions to survive data center failures. Modern cloud platforms provide multiple isolated locations, and leveraging them protects against regional disasters. Third, stateless application design builds applications without session state stored locally on servers. This enables seamless horizontal scaling and failover because any server can handle any request. Users can be redirected to different servers without losing their session or experiencing disruption. Additional best practices strengthen system reliability. Automated backup and recovery implements regular automated backups with tested recovery procedures to restore quickly from failures. Backups are only valuable if recovery procedures are tested regularly and teams know how to execute them under pressure. Capacity planning and scaling designs auto-scaling mechanisms to handle traffic spikes and maintain performance during peak loads. Systems should automatically add resources when demand increases and remove them when demand decreases. Chaos engineering regularly tests system resilience by intentionally introducing failures in production-like environments. By deliberately breaking components, teams verify that redundancy and failover mechanisms work as designed and identify weaknesses before real failures occur. Always-on architecture represents the ultimate in high availability, combining multiple strategies for zero-downtime operation. This pattern uses active-active deployment, where multiple regions actively serve traffic simultaneously with continuous data synchronization. Unlike traditional disaster recovery, where a secondary region sits idle, always-on architectures keep all regions active and serving users. Global load balancing uses DNS-based routing to direct users to the nearest healthy region for optimal performance. If one region fails, traffic automatically redirects to other regions without user impact. Continuous replication maintains real-time data synchronization across all active regions to ensure consistency. Zero-downtime updates use rolling deployments and blue-green strategies to enable updates without service interruption. New code deploys gradually, and if problems arise, traffic instantly switches back to the previous version. Let's summarize the key concepts covered in this video. First, high availability requires redundancy, failover mechanisms, and load balancing working together as an integrated system. No single component provides high availability alone. It's the combination that delivers reliability. Second, fault tolerance enables systems to continue operating despite component failures through techniques like replication and graceful degradation. Third, always-on architecture combines multiple strategies for zero-downtime operation, keeping all regions active and automatically handling failures. Fourth, continuous monitoring and testing are essential for maintaining high availability. Systems must be constantly observed, and failure scenarios must be regularly tested to ensure resilience mechanisms work when needed. Building highly available systems requires upfront investment in architecture, but this investment pays off through improved user experience, reduced business impact from outages, and competitive advantage in reliability.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.